economics and in physics in Milan, and then followed that up with a master's degree in physics at the University of Sapienza in Rome, and a PhD, which he received in 2015. I guess you were jointly in Pisa and in Florence somehow, but probably your was in Florence. Lucio, studying wonderful fermion atoms and lattices for many-body physics. And then he moved on to do a postdoc in the group of Chris Monroe at JQI and the University of Maryland. He was supported as an intelligence community postdoctoral fellow there, and did transferred from neutral atoms to trapped ions. And after a few years as a postdoc, and I guess a year as a visiting scholar at Oxford, or
3 months.
a few months as a visiting scholar at Oxford, he moved on to his faculty position at Rice, where he's been since 2020. And there he's established a research program, so far focused on quantum simulation with trapped ions, and he's received numerous awards, the NSF Career Award, ONR Young Investigator Award, the OE Early Career Award, and we're really excited to hear today about this latest work.
Thanks so much for the introduction. Thanks so much for the invitation. It's really a pleasure to be here. It's been very fun so far. So today I'm going to discuss a topic that I'm really excited about. Is a research direction that we have recently in my group, and it basically tries to establish a connection with my bread and butter, which is trapped atomic ions, and models that are of interest for quantum mechanics. So in particular, I'm addressing the general phenomenon of molecular electron transfer. So here's the outline. I've been told that I should start pretty broad, so I will give an introduction about trapped ions so that everyone is on the same page. So I'll show you how they can realize natively spin-boson models, in particular distributive spin-boson models, and why this is important for chemical dynamics. And then I'll try to discuss these 3 works. So one is fresh off the press, was published at the end of December last year. So 2 weeks ago. This one should be on the archive soon. It's kind of a theory follow-up to the experiment. And then we have also some preliminary data on a experimental follow-up involving more than one bosonic mode in electron transfer model. And if I have time, if time allows, I'd like to share with you some more of the technical work that we're doing. We're working on a new type of trap and a new experimental apparatus. And we also have some interesting results on how to create a beam array that is programmable both with phase and amplitude, with the goal of creating hydrogamma domains. So let's start from the beginning. So you want to trap a bunch of charges. You will not be able to do it with static fields because of Gauss's law. So if you have a 3D region, every electric field line, the static field line, will enter and then exit. So you always have a direction that is anti-trap. So the way we get around it is to use inhomogeneous time varying. So here you can see exactly what happens, at much faster time scales and smaller length scales in the time trap. This is in the radial plane. So we apply this quadrupole and effectively we create an effective harmonic confinement in the XY plane. And then we apply weak static confinement along the z direction to basically create the shape. So now that you have this equilibrium position, you can see that these ions repel each other because of the Coulomb interaction. So they're the distance of the order of a few microns, so they're easily resolvable. And if you go to second order, you can actually see that the competition between the harmonic confinement that you apply in 3D and the Coulomb interaction gives rise to harmonic. So you can write this with a very good, there is an approximation here. Of course, there are also higher terms. But to a very good degree of approximation, you have a bunch of harmonic oscillators, so you can quantize. You have actually 3n of them, so 2 Trangus modes and one set of Hassel modes. And just for starters, the typical frequency scale is like megahertz for the radial mode, tens or hundreds of years for the axial, for the central mass. So this is just a cartoon, but if you go in the lab and actually measure a long chain, you actually can resolve each one of these. The 32 ion chain And if you do spectroscopy, you can see 64 radial nodes. So you can think about it as this ion crystal as a kind of a macromolecule where you know very well each vibrational mode, you know how much each ion contributes to each mode, because basically it just depends on the harmonic confinement and the fluid structure. It's a classical, efficiently easy problem to solve. What are these eigenvectors and eigenfields? So now this is for the external degrees of freedom of the system, the neutron. So now, what about the qubit? Well, in ions, a few years ago, you had only two options. You can either, go old but good old hyperfine qubit. So these are the most common qubits used in ions used in the community. Or you could use a metastable excited state here that has different lifetimes depending on the ion you choose. But recently people realized that you can also use this metastable state. If it has an hyperfine structure, you can actually just use that as a qubit. So you have three different types of encodings, and interestingly, all the ions have the same structure, except these two that are very light and they don't have this metastable states. But all the others, they basically like alkali atoms, just group 2 atom that restrict one atom. So, this is now called OMG architecture, which is not oh my god, but it's actually optical metastable ground. And so this is for the, for in general, in my lab we use ytterbium. So ytterbium is very nice because it has all three qubits. So most of the work done so far in quantum simulation and computing is basically done using the ground state qubit. It's very nice. It has a 12.6 gigahertz splitting. It has been demonstrated that T2 with dynamical decoupling can reach 10 minutes. It's probably the world record. But in the lab, if you don't even try, you get of the order of 1 second. So it's pretty good. You can prepare it in tens of microseconds with optical pumping, coherently manipulate it with Raman transitions, and then detect it with just spin-dependent fluorescence. Right? So if it's projected up, it's bright. The many photons projected down is dark. So now on top of that, we also have optical qubits. So actually, ytterbium has these 2D states that are quite interesting. They can be used as clocks, but they have fairly large matrix element to be a quadruple transition. They have lifetime of about tens of milliseconds. So you can get only 10 to the minus 15 basically accuracy in the clock. But they can, because they have pretty strong rapid frequencies, you can easily get cooling, and we'll see in the following how to use this state. Or because these are pretty large matrix elements, you can actually do a Raman transition on a particle state. And that's actually pretty interesting because it turns out that you can create effectively light shift gates on a clock qubit, which was thought to be hard to do. I'll touch that later. On top of that, ytterbium is a very special atom because it has, being heavy, before the S shell, it has a completely filled F shell. And so you could actually, the first excited state is basically one of these F shell electron that is promoted to the S and creates a closed S shell with a F hole behind. And so you have this electrical configuration here that gives you a very, very long lifetime. So this state is years of lifetime. So it's really like probably the most metastable optically excited state that is out there. And you can use it to do partial measurement or qubit calculation. So in the following, I'll show how we master this, different squares of this toolbox, but we're progressing on using all these optical states for different purposes. So now we discussed external degrees of freedom, internal degrees of freedom, like how we decode a qubit. Now we're going to put them together, and that's very important if you want to do gates. So I don't have the time to actually do full derivation, so I'll just give you an intuitive picture of how you perform gates in product. So you want to entangle this ion here that are at a distance r. You shine two beams that apply a spin-dependent force. So that's the key. So if the ions are in the up state, they move in one direction. If they are in opposite state, they move in opposite direction. Okay. So how would you write the Hamiltonian? If you have a spin-dependent force, well, that's a force times a displacement, which is spin dependent, so it's multiplied by sigma c. So you displace up in plus y or minus y, depending if you're up or down. And so if you quantize this, this position greater, then you get effectively a spin-boson model. So that's the idea. Yes.
I'm curious because I know like in graphite, typically it will be like sigma plus some kind of like
it's got
the sigma z.
It's got it. So so you can do both. That's the nice thing about it. So it's very similar in cold atoms, very similar to do Bragg spectroscopy or Raman spectroscopy, right? Like if you do Bragg, you effectively apply a sigma z. You basically light shift in different ways. So it's a spin dependent light shift. But you can also flip the spin, and that's a sigma x or sigma y. And so if you actually apply a sigma x or sigma y, this picture is exactly the same, it's just in the rotated basis. So if you are in plus x, you displace in one direction. If you are in minus x, you displace in the other direction. But the physics doesn't change. So and you can do both. Okay. And so of course, if you time it right, this phase can be fiber 2, so it's a fully entangling gate, and that's basically the input. So now, that comes exactly the sigma plus sigma minus. If you now, instead of applying a light shift, you actually apply, which is somehow more intuitive because it's the z basis. If you apply basically a spin flip with two Raman transition that are bridging the gap of the upper prime qubit, then you effectively can create, you can either flip the spin with the carrier if they're resonant with the qubit, or you can create this native Hamiltonian. You can have a James Cameron Hamiltonian where you trade a vibrational excitation for a spin, or you can have also the anti-James Cameron. So we call this red and blue silence. So now if you combine the two, you can see that sigma plus and sigma minus multiplies A, and you have effectively a sigma x times A plus A double. Okay, so this is the native Hamiltonian of the system in a certain rotating frame. You can choose whether to apply sigma x or sigma y. Of course, on top of that, you can also control the effective frequencies of this harmonic oscillator by changing the tuning. And you can also apply single body rotations along both three directions. So now, if you go to the regime where this spin-phonon coupling is much smaller than the tuning from the motional mode, you can show that effectively you get a spin interaction. So this is very similar to, for example, what Monica does. In that case, you have a visual photon that is exchanged between two spins. In this case, the visual phonon. So a phonon gets emitted from one ion, travels, gets absorbed by the other ion, and you have this antiferromagnetic interaction right here. Now, the nice feature of ions is that because you have this vibrational modes that have basically the long range interaction baked in them, you get a long range capacitor to the spin-spin interaction. And this alpha is actually tunable depending on how far you detune from the center of mass. You want to be more long range, push it closer. You want to be short range, push it further away. And there are also other turning modes. So that's another handling the toolbox. And finally, if you apply a very strong drive in one direction of the block sphere, you can actually preserve the number of excitation in that direction. So you can effectively create an XY model or a spin exchange Hamiltonian or flip-flop Hamiltonian, however you want to call it. So you have, these three Hamiltonians are basically kind of what you can do with ions. So now, why this is interesting? Why is it related to electron transfer reactions? Well, let me take a step back and give a very, very general introduction. So electron transfer are everywhere in life, in biology, chemistry, physics, etc. And usually, generally speaking, is just an excitation on a donor side that has to hop on the acceptor side. And the whole thing happens in a very messy environment. In biomolecules, you have this protein scaffold with all the different vibrational modes. You can have a solvent, so it can be very messy and wet. And this can be direct, or you can have many intermediate states depending on the system. So what quantum chemists do, they basically use the language of over quantum to model this type of processes. So they cut the boundary of the system at some point, because otherwise it would be too messy to treat everything exactly. And then you find a way to basically model the environment in different ways. You have hierarchical equation of motion, you have gradients, there are many groups. So now, why this is related to quantum effects? You might say, well, but if the system is at room temperature in this, this type of electron transfer reaction, then why do you even expect to have some role of quantum coherence, right? Well, it turns out that already in the 60s, actually, and the 70s, this is the same John Oppenheimer who won the Nobel Prize, by the way. So people started to realize that the typical classical behavior, that is the Arrhenius transfer rate, that is thermally activated, is actually affected by tunneling, by quantum tunneling when you lower the temperature. And you would say, well, but you lower the temperature. Well, I mean, in some cases, for example, this electron transfer from cyclotron to chlorophyll, you actually have that this cutoff temperature is of the order of 250, 200 Kelvin. So it's actually quite close to room temperature. So it's not too far. And also, in 2007, there were this pioneering experiment where they did 2D spectroscopy on FMO, which is a light harvesting complex, and they saw that there is this coherent beating, as a function of time, of this exciton. And still to this day, it is debated whether these excitons are actually coherent or they're just seeing vibrational coherence. So they're just seeing Raman, and what you see is just two different vibrational modes that beat against. And this actually was seen in 2014 even at room temperatures. You can see some oscillations. So the question is, there is an open question there, like, is there a role of coherence in this electron transfer? That's why it's so efficient in, for example, photosynthesis. And what is the origin of coherence? It's purely vibrational, and so it doesn't have any effect, or is electronic, which sounds crazy because electronic dephasing is very fast, or maybe it's vibronic. So you have a coupling between spin and electron, and actually the vibrational coherence have an effect on this exciton. So now what does this have to do with ions? Well, if you put together all the toolbox that I told you about, so you have a spin exchange Hamiltonian, you have the capability to create local line shift to basically paint energy landscape, and you have native normal modes of motion with spin-phonon coupling, then you basically have all the ingredients to realize the models that people use in this field. Okay, so they use exactly this model. And on top of that, of course, these modes are part of, they're in touch with, they're basically in contact with their environment. And so we'll treat that later. So it is a very complicated system. And in terms of numerics, you might ask, well, is this actually, hard to treat? So it's not really this part, because usually they work in the single excitation manifold. So you don't really have Fermi statistics. You have just one electronic state that hops around. But you have many modes of motion, and you have dissipation. So actually, to treat the system exactly is very hard. So there is this recent review that showed that, for example, when this quantity here, the ratio between the spin-phonon coupling squared and the typical vibrational mode is large, then it's of the same order of the electronic hopping between different sites. It's actually pretty hard to compute the numerics, and maybe trap time simulation have an edge in this regime. This is called the intermediate regime. And numerically, you can try matrix product states or operators. And in this case, in this paper, I believe they did tens of qubits with tens of modes, but that's using several days of computation. So it's pretty. So now. Let me go to the actual experiment that we did. So the first thing that we did was actually to strip down the complexity to the most simplest case, where you have only two sides, donor-acceptor, so you have only two states, and so you can map it to just a single group. So donor-acceptor in this case is up and down. You have a reaction coordinate that is given basically by your motion here. That's kind of the spin-dependent force that we discussed before. And you can, you have the energy difference of electronic coupling, and then you have that basically there's a spin-dependent displacement between this donor and acceptor. So the donor is displaced in one direction, the acceptor in the other. And if you write down the spectrum of this Hamiltonian, effectively you have vibronic states. So you have you can be in the donor state, and you can have the wave packet that is displaced in one direction or the other, and they are basically coupled. They are displaced by this G. So this G over omega is the displacement between the two, let's say, Born Oppenheimer surfaces, and the omega is the vibrational level. And then the difference in energy between these two wells is the sigma z terms, and then the splitting basically opens the gap. This is reminiscent of some spin orbit coupling that people were doing 10 years ago. But with the difference that the motion here is quantized, because you have discrete vibration levels. This is not only a VC in a spin orbit coupling. So you can, of course, tailor and characterize all these terms individually. This is just a Rabi oscillation. The spin-phonon excitation, it's a little bit more complicated, but it's actually easy to calibrate. And we do this using the Brownstein qubit. So we use the Raman transition, and we have one mode and one spin, so it's not very complicated. So now, what is the new ingredient that we added? Well, the thing is, this is not the end of the story. This is just a system, but then in this electron transfer models, you have a bath. So you have a bunch of harmonic oscillators that are like out there, and they are coupled linearly with your reaction coordinate, your boson. And so the nice thing is, and maybe they have a certain spectral density, like for example, ohmic spectral density is a typical choice for this. So now it turns out that in certain regimes where the relaxation rate of this bath is actually smaller than the typical vibrational frequency, and it is smaller than the temperature of the bath. H bar gamma is smaller than the temperature of the bath. You actually can do an approximation and treat these complicated dynamics with the Lindbladian. And so this Lindbladian is very familiar to quantum optics and hemophysicists, because it's basically the cooling Lindbladian. So you basically relax to a certain n bar, which is your steady state here, with a certain rate gap. And we can do this by using the other qubit, the optical qubit, because it has a strong enough matrix element so that we can cool it down. And most importantly, we have enough handle so that we can choose gamma. We can actually tune the relaxation rate of our bath. In principle, we can also choose the steady state, but we didn't do it. We went to just very low temperature. So we have, to sum up, this is the system. It's a cartoon of the system. We have one ion that encodes the spin and encodes this Hamiltonian here. We have another ion that has provided an optical qubit that we can use for cooling. And the cooling is on the same mode that we're driving. So because it's a shared mode. So if we cool this guy, we'll also cool the collective, right? So, and we have 5 parameters that we can tune, and that gives us a lot of flexibility. So, just a single side note, we use 172 here just because it's spectrally resolved, and there is no crosstalk at all between these two unless you put some spin-phonon coupling. So you can drive the qubit here while cooling, and there is absolutely no crosstalk because this line is very important. So, so what happens if you now switch on the dynamics? You prepare a certain vibronic state at the beginning here, and you set the energy, the internal energy, to be resonant with the vibrational energy. And so what happens is that these two states oscillate if you don't have any dissipation. Of course, there is some decoherence in the experiment, but this is not a simple Rabi oscillation. It's actually oscillating with a frequency that is proportional to the electronic coupling here, but also to the overlap between these two displaced harmonic states. So this is basically the Frank quantum factor in chemistry. If you switch on now dissipation with the optical qubit, you see that effectively, intuitively, what you're doing, you're giving a tunable line width to these states, and so they basically relax from one side to the other. And this is not really, you don't have to think that we're optically pumping, because actually we operate in the rotated basis. So basically, we're effectively motionally assisted pumping the plus y state to the minus y state. Okay, so the coherence in a sense is preserved of this superposition. So And here you can see that we have a reversible transfer when we are resonant. When we're not, this doesn't happen, or it happens at a very much slower rate. So this is kind of the experimental sequence. So we apply, we prepare both the spin and the motion state. So we apply a power 2 pulse, and then we displace the motion state in one direction. So we are on the donor side in phase space. And then we apply both the Hamiltonian and the dissipation at the same time. And then we undo the rotation, and we measure the y basis. And so we can address, well, I commented on this already. So we can actually, we are in the low temperature regime. So the steady state here is pretty low in N bar, is like 0.1, 0.3. So the temperature doesn't really play a big role. We didn't explore that direction yet. So there are basically two extreme regimes that we can explore. One is when this Vx here, this electronic coupling is very small. So the eigenstates of the system are well described by localized vibronic excitations, right? And so this is basically Vx small perturbation, and you have a kind of an exponential leaking on the other side, from donor to acceptor. But if you actually increase this electronic coupling, then the initial state, that is this localized vibronic wave packet, will be actually a superposition of all these eigenstates. You have oscillations, and but then you still relax to the acceptor state. So basically, if you are in the perturbative regime, you can actually describe everything with the Fermi-Golden rule. So here you have all the ingredients. You have the electronic coupling square, the Frank condom, which is the overlap between these two displaced harmonic states, and the delta function that enforces the energy conservation, which you can broaden as a Lorentzian to include the broadening of the path. And so now we can scan. The nice thing of Einstein, you can control all the parameters. So you scan basically this well with respect to each other, and you see that depending on the ratio between delta E and omega, you actually hit the vibrational resonances in this regime. So this KT is basically the transfer rate. So it quantifies how fast you go from donor to acceptor. It's just integrating the whole dynamics. And you see that here, for example, the master equation does a much better job in explaining the data than the Fermi-Golden rule, because we're not really totally in the perturbative regime. So you can look at the heat map. So here is the time versus the energy, and so you see that you have this type of resonances, and we can even go a little bit farther from the perturbative regime. We can reduce gamma and reduce also G. Here we were pretty strongly coupled to the emotional mode, and so here we see less resonances, and also they're narrower, and they're also further away from the Fermi-Golden rule. So we can go in the strongly adiabatic regime, and this is actually a little bit more complicated now. So the spectrum looks more definitely richer. You see these oscillations that I showed you before along the first resonance. But it is way more robust. You don't see all these peaks, but you see kind of a linear increase here. And the interesting thing is that here we can do the experiment with different dissipation rates. So we can do two curves, take two data, just changing the gamma, changing the Turing rate. And we see that, first of all, the Fermi-Golden rule doesn't apply anymore. So K is proportional to gamma, because these two things collapse on each other when you plot them when K is in units of gamma. And you see that when you have very large energy difference, you actually start to see again these peaks. And so there's a crossover at this point when you have very large energy. Your initial state starts to be localized in the upper surface of this phonon parameter potential. And so this means that you start again to see what this quantization effect, that you have these peaks here. And what is interesting is that here we also see the so-called inverted regime that Marcus predicted a while back, where if you increase the exothermicity of the reaction, so you increase more and more the difference in energy, you actually see a decrease in the transfer rate. And this is due because the Frank condom gets smaller and smaller. So finally, we can also look at what happens if you tune now the X continuously. So the electronic coupling from the weakly perturbative regime where everything is quadratic, and then to the strongly adiabatic case, and we see that there is a kind of an optimal regime. And this was predicted, in '92, this model that is actually a little bit simpler than what we have here because it was phase. But in general, the fact that you can have, an optimal amount of dissipation is something that is kind of intuitive, and because you can relate it to, for example, impedance matching, right? You want to go coherently on the other side, and then you want to just be critically coupled effectively and be, kind of damped very quickly. If you drive it too fast, then you will oscillate. If you drive it too slow, then you will leak very slowly, right? So it's kind of like a critically damped harmonic oscillator. And what people think is that maybe nature actually optimized to be in this regime that is not robust, that is close to optimal, so that it just gives the right amount of dissipation in all these, different systems like solid states or biomolecules. So now, we didn't do this in a vacuum. We actually started here on the West Coast. This is kind of the first experiment that tries to make a connection between, ions and electron transfer models using the spin-boson models. And then Duke and Sydney also did many experiments. Actually, in the right when we posted the paper on the archive last year, we were contacted by Johnson Kim, and actually he had very similar and complementary result. Here they use randomized rotations to induce effective dephasing. But they have more, for example, flexibility on the spectral density that they can choose for this path. So they can actually go from ohmic to super ohmic to subohmic, which is very cool, and it's something that we're interested to do too also with this cooling case. So to summarize, let me say that we have set this non-perturbative optimal regime, but the main thing is that this was really a interdisciplinary collaboration. I spent basically 1 year trying to find a common language with chemists and biologists. I think this is the way to go because it is very rewarding. And now we have many ideas on what to do next, right? Because you would like to simulate things that are closer to nature. And in nature, you have, for example, the LH2, that the light harvesting complex 2, that is basically this messy system that has different monomers. Each monomers have multiple molecules in it, like this is 14, for example. And this is a simplified structure because, for example, if you look at this FMO, you have only 8 sites, but they are, in this messy environment that is the protein scaffold. That also people think that is actually important for electrons. So how do we actually get there? Well, to encode more sites, I think the way to go is to add more qubits. And to actually, to encode the environment, we need more bosonic ones. And so we're going in that direction right now. So this is kind of a theory follow-up on what we did. So we ask ourselves, you have this very complicated system, and you can write down the Hamiltonian. What is the minimal system that we can do with trapped ions where you have delocalized excitations or excitons. So you have basically excitation over multiple sites. And you have a vibrational environment where we can tune the relaxation. And actually, way to do it is, is just to start in this simple model where you have, Frankel exciton. So Frankel exciton are basically excitons that are delocalized in a few molecular sites. They are basically living on this, on either the donor or the acceptor side. So you can have an excitation that is delocalized here. And because we have inherent native long-range interaction, you can actually put 2 coulomts in between so that you basically mimic what happens in these systems where the intramonomer coupling, the dipole-dipole interaction, of course, between molecules is much stronger than the intermonomer, right? So you can have a still appreciable long-range interaction between this donor and acceptor, but smaller than the J. And so we basically here to just understand what is the physics, you can draw the same diagram. Of course, it's more complicated than this because you have more states, more spin states. And if you are in the perturbative regime, you can actually write down the Hamiltonian in the following way. You can use the so-called exciton basis. So you can rewrite, instead of using the product states, you have only 4 states. because this excitation can be in 4 different sites. You can actually write it down in terms of triplet and singlets, and or symmetric and unsymmetric states. So this is a perfectly complete basis. You can write down the Hamiltonian in this basis, the spin Hamiltonian, and what you get is that basically you have different coupling between triplet states in different positions, or triplet to singlet, or singlet to singlet. And what turns out is that because of long-range interactions in this kind of open system, you have that the JTP, the chain that connects two triplet states, to triplet basically superposition or entangled state, it's much stronger than the other processes of any other process. So effectively, what happens is that in the perturbative regime, you transfer this bell pair from one side to another just by switching this secretive system, this Hamiltonian plus dissipation. And so what is interesting is that having this localized state actually enhances the transport compared to having just an excitation, for example, right here, just a product state, which is pretty cool. So in the perturbative regime, everything is explained by the Fermi-Goldberg rule. So this is kind of similar to what we saw before. In the non-perturbative regime, there is more stuff happening. I don't have the time to go into the details. We can discuss it later. But you do have the same behavior, basically, that you really transfer this entangled state, this bell pair, from one side to the other. Okay, and you do it distributed. So the relaxation rate is interesting. It has a non-monotonic effect on the transfer rates. You can see that here, increasing the relaxation, you actually can increase the transfer rate, or can stay the same, can increase. So similar to the previous case, you have an optimal amount of dissipation. It's kind of the same physics. But what is interesting now is that we can, build up the complexity. Again, this is fully numerical, but you can, ask yourself what happens if you have more, for example, a monomer that is more complex. So can you, how does it scale? Well, it turns out that if you write down the long-range interacting system here, you have an ion state. The largest energy donor exciton state is actually very close to a W state, where you have a symmetric superposition of all the excitations. And so you transfer this W state very, very effectively and much faster than any other product state. So in this sense, also the localizations. And you can see that you have also, if you put a bunch of them, you can transfer from one edge of the chain to the other, this bell pair, in a purely distributed way. Of course, you have to tune the energy. So now this is for more qubit stuff. So we're building an experiment to do exactly that. But what we can do right now with one ion and two, we actually have 3 n normal modes, right? So if you have 2 ions, you have actually 6 normal modes, right? So you could use another one of those to encode a 2-mode system. So we can add more, tones to our AWG and drive the spin-boson, couple the spin to not 1 but 2 modes. So we have now 8 parameters, because we can also tune the dissipation. We can cool both modes at the same time with tunable dissipation rates. So now the parameter increases significantly. It was 5 before, now it's 8. So we're still working on this. We're still trying to get a handle. So the first thing that we study is just symmetric. So we just put the 2 modes together. And in this case, the classical Born-Oppenheimer surfaces, they are like in 2D. And what happens is that basically the reaction coordinate effectively is just moving from one side to the other. But we already started taking data, and it looks fairly interesting. So if you have 2 modes, effectively you increase the transfer rate compared to the 1-mode counterpart, and you still see this adiabatic regime, this localization peaks that arises. But what is more interesting is, for example, what happens if the 2 modes are actually different in frequency. So in real system, in this, you have to imagine that you have this, monomers where you have these molecular sites, and these molecular sites, they have the intermolecular modes that are much higher frequency than the solvent modes, right? So they are more coherent, but the solvents is, it's much lower frequency, so it's easily to be delocalized. So the take-home message here is that, if you have one mode that is coupled to the spin excitation, that is like lower frequency and heavily delocalized, given that the electronic coupling is the same, you actually can see that instead of seeing these peaks, you actually kind of fill the gap. And the idea here is, even if these two are now not resonant, the fact that in this direction here, it's hard to visualize, but you can fold it in 1D. In this direction here, you have this very broad wave functions because this omega is much smaller. It actually helps because the different component is larger and you basically have a more robust transfer rate. So that's kind of preliminary. I mean, this was taken a few days ago. So it's kind of very, very rough. So, there are many directions that we, I'm not doing on time actually. Okay. So what is the time usually like, I should finish by 15 or?
Yeah, you have a few more minutes. Yeah, we want to be totally done by, so like finish by 50.
Okay. All right, so there are many, directions that we want to explore. One is the spectral density engineering, so that will involve having multiple nodes and cooling rates. Another thing that is interesting, I think, is to couple different bosonic modes, and this is really unexplored even for theoretical chemists. Something that people didn't really explore too much, but in ions you can actually have this type of accidental resonances between two different nodes, and you can have this nonlinear coupling. So to include the harmonicity is actually something that would be very interesting and makes the classical theory very hard. We can study effective temperature, and more in the more condensed matter spirit, you can drive now multiple nodes and realize the spin-boson and Hamiltonian, where you can see things like superconducting transitions. I mean, in this case, it's a little trickier because you have many excitations. You exit from this, one excitation manifold that makes things easier. But it's a very interesting direction for collaborating with Eugene Denver. So now to access this wonderful physics, we're building a new system. We have an array of optical beams where we control in phase, amplitude, and frequency. We have an upgraded vacuum system, and we also have a new trap. So I will touch a little bit on this because we've been collaborating with the company to basically put together the best of both worlds. So in trapped ions, if you're not familiar with the trapology part of ions, there are basically two approaches. You can either have a end-of-line three-dimensional structure that is very robust, it's easier to use, but it's not very reproducible. Actually, it took for quite some time to have this trap to work properly in my lab. Or you can go for this microfabricated trap that are more scalable, they're definitely more reproducible, but they have lower trap depth and they can have also other problems. And also they're not, from the practical point of view, they're not very accessible by commercial. So what we're trying to do is together with my colleague at Duke and this company in Michigan, Translum, we're basically using their technology to build a microfabricated three-dimensional blade trap. So this gives you the same optical access of this one, the same robustness of the potential, but also all the kind of reproducibility advantages of this microfabricated techniques. And it's actually, it's not bulky. This one is this big. It's like a 10 centimeter, and now it's much smaller. There are some, things that we're optimizing to make it work properly. Unfortunately, they do everything with few silica slabs, and they create this kind of Michelangelo structure with laser writing and etching. But few silica is a very poor term conductor. So once you drive the trap really hard, here we're trying it with 1 kilovolts. Actually, here we tried it with 1.5 kilovolts, peak to peak, at fairly high frequency, and usually the driving uses about 30 megahertz. You can get, for example, that the trap glows visibly. So it's not great. So we did a bunch of improvements to geometry of the trap and also to surface cleanliness, and now it looks a little bit better. On the good side, you have a microfabricated trap, you predict, simulate a certain potential, and you get exactly that. So all the frequencies are read very well with the data that we expected. But there are also things that are not working exactly the way we predicted. So for example, we have axial micromotion. This means that there is an RF field that is kind of residual, and we know how to explain it. So we think that it's due to both the asymmetry of the field itself and also to some asymmetric peakoff that we have in the structure itself. So now we kind of waiting for this new generation of time where everything is very symmetric and there could be absolutely no symmetry and no accident. So let me remove my academic hat for 1 second and just advertise this because it's been something that I worked on pretty hard in the last couple of years. So we actually founded a company to provide ion-trapping systems. It is based on this this trap that makes the assembly much faster and cheaper. And so we have a bunch of now these two products, and we're working on this now to make it even more compact. And we had the first funding round, and the first system will be installed hopefully this year. So if you ever want to start an ion trapping group, let me know. Anyway, coming back to the science. So one last thing that I'd like to mention is, like there was an interesting question between having ZZ interaction or XX or YY interaction, right? So wouldn't it be great to combine the two, right? So it would be nice to use the radial node that we're using now to do spin-boson model that eventually we want to use to do this spin exchange interaction with some CC interaction, right? And you can use in principle axial modes so that the two things are completely unrelated and you have tunable control on both. But this means that you have to apply a spin-dependent force along the axial direction. And so, and then you have to also have control of the phase of this axial gradient. So for example, what we're exploring is to create an array of beams of TM01 modes so that the gradient along this direction actually give a peak in the transverse direction of the light instead of the usual longitudinal kick of the photon. You have a beam that hits the ion like this because you have basically you have orbital angular momentum, so you kick also the ion. So to have both control of the phase and the amplitude, we actually found this interesting algorithm that is kind of an extension of the usual Gerber-Saxon algorithm that people use in tweezers. That algorithm basically gives you uniform intensity, but the phase is completely random. So here we can actually control both of them by basically doing kind of a two iteration of the inverse Fourier transform, and we have pretty good control over the phase, and so we can ensure that the amplitude is the same and the phase is programmable. Basically, we have alternating phase or uniform phase or kind of random arbitrary phase, and the efficiency is pretty good. Actually, it's like 50-60% at UV wavelength, so it's pretty good. And it works also in UV. So here you can see that we have an array of TM01. We can flip the phase and make them alternating. Here is uniform, or we can do this in UV, and it works pretty well. Of course, there's a lot of work in correcting for operations stuff. But all right, and with this, let me thank my group, the four grad students, Sal, Muna, Abhishek, and George, and the undergrads, and there's a postdoc opening if you're interested, because Roman is the research scientist that is frontman of the company who will transition there now that things are taking steam. So thank you.
So I guess one of the directions you want to push on here is the scaling of the atom number in order to treat these sort of highly more complicated systems. But do you have some understanding of sort of your accuracy as a function of n for being able to predict this, and if I guess how it scales versus estimate?
Accuracy, you mean in which sort of?
I guess in terms of whatever sort of final chemical observable you're trying to predict.
Well, in this case, I think is we're not trying to we're not at the stage where we're trying to predict like an energy or like parameter, but it's more like to try to find qualitative schemes to, for example, enhance the transfer rate. Like here, for example, what we found is that having long range coupling actually helps in certain configurations. So the idea is more on the qualitative side, I would say, than to predict with the required accuracy. I don't think that I have strong opinion also of all the electronic structure type of direction that people take that, oh, you want to be at the chemical accuracy. Talking to my colleague in quantum chemistry, they are very skeptical that this will ever happen, that quantum computers will actually be competitive with classical methods in terms of chemical accuracy. So I think the best way to go is to just do some analog simulation of models that retain some of the physics at a low, let's say, qualitative, low rank observer, let's put it this way, and not like some type of very, very tiny effect in tiny shift in the energy or something like that. And so here we're basically estimating the transfer rates. And so I don't have a good answer to the accuracy.
I guess my question is just like these like low rank observables, like you have some like feeling about I guess the scaling versus the intent methods. I guess my point is that these low rank observables, that's also again test methods should also be relatively good with low quantum dimensions, low classical simulation costs. So I'm wondering what the cost benefit there is.
Yeah, so it's a very good question. It's not clear to me because ECMTS method work, they have been used, for example, the exciton, they've been used for short range. So they haven't been used in long range systems. So the hope is that when you start switching on this long range coupling, then maybe MPS don't work as well. On the other side, you have dissipation. Dissipation definitely can destroy can basically limit your Hilbert space effectively, and so that is an argument in favor of using this MPS. But the dissipation right now that we're using is on the Moshfeld mode, and the Moshfeld mode actually preserves basically it's a sigma z coupling that commutes with the orthotropic states. That's why you don't destroy the entangled state, because you're basically dissipating a CELA effectively that is coupled in a way that doesn't change the spin state. So I think it remains to be seen. But yeah, it's a good question.
Regarding the laser cooling that we do, I have no experience with ions, just with atoms. I just know the question is whether this really brings you from equilibrium. I just know from laser cooling atoms, you have some temperature, and the atoms don't fly directly after the cooling. It's far away from thermal equilibrium. So the question is, how close is it to the spin? Boson assumes that you have such a spin orbit coupling, and then it has to be thermal equilibrium, as I understand. So how is it in ions? Is it after you laser cool, so the forces of the ions directly to the atoms? What this gives, at least for atoms, it doesn't give you thermal. So how is it?
So your collision don't give you thermal equilibrium?
Well, I mean, you do laser cool, but afterwards the forces of the lasers to the atoms that has to do with the resonance profile, and this whole system it cools down your atoms.
So you're saying like an optical molasses is not in thermal equilibrium, that's what you're saying.
Right, it's far away. Yeah.
Okay. Well, in this case, I mean, you can actually do a careful spectroscopy on this, average number of phonons. So I guess you can relate the temperature to the average number of phonons just through the Bose-Einstein distribution.
Mm-hmm.
Okay, so what we measure directly is the average number of phonons. Mm-hmm. And so we can measure it very precisely by basically driving this James Cumming or anti-James Cumming Hamiltonian. So you basically do a kind of a red side and flop, and you can, depending on the state of the Moshfeld state that you have, you can have a squeeze state, a thermal state, a display state. You actually see a different dynamics. Mm-hmm. And so usually, by taking those data, you can convince yourself that you are in a thermal state with a certain N bar. And you can see here that maybe this